Hello everyone, my name is Matt Just and welcome to my talk. Today I'm going to be discussing the Fibonacci numbers and their connection with the golden ratio. Now this is something I think everyone who has an interest in math should know about. So the outline is going to be we're going to introduce the golden ratio if you're not familiar, give a little bit of historical background, and then discuss the Fibonacci numbers. And then finally what we'll do is we'll prove a very cool theorem that connects the Fibonacci numbers with the golden ratio. Okay, so what is the golden ratio? Does it have something to do with gold? Is it the density of gold? Density is a ratio. It actually doesn't have anything to do with the element gold. It has to do with a particular ratio of two distances. And now this goes back to the ancient Greeks. A lot of people believed that a lot of the art and architecture that they used were based on this ratio. Some even say that the builders of the pyramids in Egypt used the golden ratio to make certain dimensions in this ratio. But we're going to give the definition in terms of a rectangle. So here's my rectangle right here. It has a length, which we'll call L, and a width, which we'll call W. And so the length and the width of this particular rectangle are said to be in the golden ratio if the following is true. So the length to the width, that ratio, is equal to the ratio of the width to the sum of the length plus the width. Okay? So that is the golden ratio in a nutshell. Now, some might say that the optimal rectangle in a lot of cases is a square. So we'll see very quickly that the ratio of the length to the width is not 1 in the golden ratio. It's a little bit different. But somehow there's some sort of aesthetic quality that is very positive. It looks very nice when you have the length and the width in this ratio. So let's actually see what exactly numerically the golden ratio turns out to be. Okay, so here's the proportion that gives the golden ratio. Now what we're going to do is we're going to try to find the numeric value, sometimes called the value of the ratio. And we're going to do that by solving for the width in terms of the length. And so how do we do that? Well, we're just going to do some really simple algebra. So as long as you remember how to solve an equation like this, do some cross multiplying, and then use the quadratic formula, we're going to be able to solve for the value of this ratio. So let's cross multiply. So we'll do the width times the width. That's going to give us the width squared. And then on the other side, we'll have the length times the length plus the width. Okay, and we'll just do some rearranging. So we'll distribute in here. That'll be length squared plus length times width. And then we see that in the width variable, we have a quadratic equation. So what I'm going to do is get everything on one side, get it into kind of a standard form for a quadratic. So I'll subtract over this term, length times width, and then subtract over the length squared term. Okay, and that'll be 0. Okay, so now we have sort of our coefficients a, b, and c. A is 1, b is negative L, and then c is negative L squared. So what does the quadratic formula tell us if we want to solve for the variable w? Well, w is going to be negative this coefficient, so that's just the length. And then we have a plus or minus. Now we'll actually have to make a choice. We'll have a positive value and a negative value. Of course, for a ratio, we want to take the positive value. So then we have the square root of, okay, this coefficient squared, so that's the length squared, and then minus 4 times the product of these two coefficients, but one of them is negative, so we'll get a plus 4, and then we have another factor of length squared, and then all over twice the leading coefficient, which is just 1, so over 2. Now what we can notice is that we can actually factor out the length, right? So we have the length here, and then underneath the square root we have the length squared. Now the length is positive, so when we pull the length squared out, square root of the length squared will just be the length. So what we get is that the width is going to be, we'll have a 1 here, we'll have a 1 plus 4 here, so that'll give us a 5. So we have 1 plus or minus square root of 5 all over 2 times the length. So what this tells us is that if we have the length of a rectangle and we want to form a rectangle that's in the golden ratio, the width should be this factor times the length. Now I told you that there's actually two values coming from a quadratic equation which has two solutions. But notice that if we subtract the square root of 5 from 1, that's going to give us a negative value. The square root of 5 is bigger than 2. So we want to take the positive value. So what we're going to do is actually just take away that negative and look at the positive value. Again, because it's a ratio, the lengths are positive, so the value of this ratio should be positive. And this number here, we're going to give it a special name, the Greek letter phi. Okay, so this number, now phi is approximately equal to 1.618. And this value is the golden ratio. All right, let's transition and start talking about the Fibonacci numbers. So most people are familiar with the Fibonacci sequence. So it starts with a 1. That's the first number in the sequence. The second number is also 1, and that kind of initializes our recursive process, because now every subsequent number in the sequence we're going to form by just adding the previous two. So 1 plus 1 is 2. And then 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And we can keep going forever. Now the nth term in the sequence will denote by f of n. And what we would like to do real quick is give a more concise definition of f of n. Now the first term, so the n equals 1 term, is 1. That's sort of our starting point. We also need a second starting point because we're adding the previous two numbers. So the second Fibonacci number is also 1. But now, for n greater than or equal to 3, we can give a very concise, what's called recursive formula for f of n. So f of n is f of n minus 1, and then plus f of n minus 2. And this gives a very clear definition of the Fibonacci numbers. So now let's think about what the Fibonacci numbers have to do with the golden ratio. So here's the central question. What do the Fibonacci numbers have to do with the golden ratio? Well, the answer is really simple, and it comes by looking at the quadratic equation, whose one of the solutions gave us the golden ratio. So recall that when we found the golden ratio, we had to solve this quadratic equation. And we found that there were two solutions. One of them was a positive number, one of them was a negative number. The positive number was the golden ratio, but they were 1 plus or minus the square root of 5 over 2. Now the cool thing is that for n greater than or equal to 2, if I take either one of these solutions to this quadratic equation, it's also going to be a solution to the equation x to the n equals x to the n minus 1 plus x to the n minus 2. And now you're starting to see the connection here with the recursive formula for the Fibonacci numbers. If I have a solution to this quadratic equation, it's going to satisfy a recursive formula similar to that of the Fibonacci numbers. Okay, so let's explore this in a little bit more detail. Okay, so let's start with a really cool observation about the golden ratio. So the golden ratio, I won't continue to use yellow for phi, but maybe one more time because it's golden, we'll make it yellow. So phi is equal to 1 plus root 5 all over 2. And that's one of the solutions to that quadratic equation, x squared minus x minus 1 equals 0. But there is another one. And I claim, actually, that it's equal to negative 1 over phi. Now, negative 1 over phi, if what I claim is true, should be equal to 1 minus root 5 over 2. So that means this should be negative 2 over 1 plus root 5. Well, let me do a little bit of conjugation, everybody's favorite thing. So let me multiply the top and bottom by 1 minus root 5. Just to clean things up. And notice the bottom is going to be a difference of squares, so 1 minus 5, so that's going to give me negative 4. And the top is actually going to be negative 2 times 1 minus root 5. And then, as I said, the bottom is negative 4. But notice that this actually is, when we cancel a factor of negative 2, 1 minus root 5 over 2. Okay, awesome. So these are actually the two solutions of our quadratic equation, phi and minus 1 over phi. And now we know that both of them satisfy this cool property. So phi to the n equals phi to the n minus 1 plus phi to the n minus 2. And then also negative 1 over phi to the n is equal to negative 1 over phi to the n minus 1 plus negative 1 over phi to the n minus 2. And this is, of course, for n greater than or equal to 2. So this sort of gives us a hint for finding an explicit formula for the Fibonacci numbers. We see that any combination of phi and negative 1 over phi raised to the nth power will actually satisfy the recurrence formula for the Fibonacci numbers. So let's go into a little bit more detail. Okay, so I have a big claim, and the claim is that the formula for the nth Fibonacci number is of this form. A times phi to the n plus b times negative 1 over phi to the n. Now, why do I think this is true? Well, based on our previous conversation about phi and negative 1 over phi being solutions to the equation x squared minus x minus 1 equals 0, it should be clear that any linear combination of them will satisfy the recursive formula for the Fibonacci numbers. So it is the case that f of n is equal to f of n minus 1 plus f of n minus 2. which is great because that's what we want. We want our formula for the Fibonacci numbers to satisfy the recursive formula. But there's one other piece of information that we need our formula to reflect, and that's the initial conditions of the Fibonacci numbers. So if you'll recall, we really also need f of 1 to be 1 and f of 2 to be 1. Okay, so how are we going to do this? Well, we know that f of 1 should be 1, so let's just plug in n equals 1 to this formula. And what we see is that a times phi plus, well, okay, so it's plus, but it's really minus, because it's a minus here, b times 1 over phi should be 1. And now that gives us an equation for a and b. But we also know if we plug in 2, we'll have a times phi squared minus b. Well, actually, that's going to be plus b now because we're squaring the negative 1. 1 over phi squared. That should equal 1. So this actually gives us a system of equations to solve for these undetermined coefficients, a and b. All right, so we're on the home stretch. So what I'm going to do to solve the system is I'm going to take this top equation and multiply both sides by phi. And let me write the result underneath this other equation. That's a times phi squared minus, well, 1 over phi times phi is just 1, so that's just minus b. And then we have phi. And what I'll do next is I'll subtract these two equations. So, of course, these two terms will cancel when I subtract. Here we'll have a b times 1 over phi squared, and then minus a negative b. So that's going to give me b times 1 over phi squared plus 1, and then 1 minus phi. Okay, so now that actually gives me the formula for b. So b is equal to 1 minus phi over 1 over phi squared plus 1. So now let's plug back in and solve for a. So we have the value of b and we want to solve for a. Now just for the sake of time, I'm going to tell you that it's a pretty easy exercise to actually simplify down this expression for b. And you find that b is actually equal to negative 1 over the square root of 5. And the reason I'm doing this is because a is going to be very similar. And now if you plug in negative 1 over root 5 in for b and solve for a, do some more simplification, again I'll let you verify, that a is actually equal to 1 over square root of 5. And with that, we can actually write down the final explicit formula for f of n. Okay, ta-da, here it is. Here's the connection between the Fibonacci numbers and the golden ratio. Now this is an explicit formula for f of n. So for instance, if I wanted to take the millionth Fibonacci number, I would just plug in n equals a million. And this is a pretty remarkable formula. There's a lot of really interesting questions you can ask. So for instance, is it even obvious that just by looking at the right-hand side here, that the output is a whole number? To me, it's really not. I mean, just look at the fact that you're dividing by square root of 5. And think about all the radicals that occur inside the golden ratio. So it really is sort of a miracle of cancellation so that the final answer is a whole number. Now, many of the properties of Fibonacci numbers that are standard can be deduced from this formula. So one of the coolest that I really like is that if you take the limit of subsequent Fibonacci numbers, so something like f of n plus 1 over f of n, you can deduce, so just take the quotient and take the limit, use all your favorite calculus techniques, that actually the limit of this quotient is equal to phi. And I would consider this to be one of the most beautiful formulas that I know of in mathematics, because it takes something in number theory, the Fibonacci numbers, and something really classically from geometry, the golden ratio, and says that they're intimately connected. So that's all I have for you. I hope that you enjoyed this talk. I'd like to say a big thank you for all of you for listening, and I would also like to encourage you to explore more of this formula and similar formulas as well. And if you have any questions, feel free to contact me. Wish you the best. Thanks again.